So we decided that we were going to use the quadratic formula to help solve that. So it's going to go a little something like this. Thank you. I knew something didn't look right. That becomes the square root of 20, right? That's 2 square roots of 5. So this is negative 4 plus or minus 2 square roots of 5 over 2, which would be negative 2 plus or minus the square root of 5. Hopefully that went okay. So I'd have negative 2 plus or minus the square root of 5. By the way, how many zeros does that actually give me? How many? I mean for the whole problem. 3. Negative 3, and then 1 with the plus, and then 1 with the minus. So that makes a total of 3. Which makes sense because, as I alluded to before, that's degree 3. Now, say what?
How did you get from
Uh-huh.
How did you get from negative 4 plus or minus that to just negative 2 plus or minus 5?
So I reduced everything by 2. So I divided that by 2, I divided that by 2. Okay. Now, something that we discussed while we were off camera, so just to give a recap for the sake of the people that have to watch the video. We were talking about how there were only 4 possibilities here that we listed, right? And only one of them actually worked. These other 2 right here weren't even on the list. How's that possible? Well, we discussed that. These aren't rational, right? They're irrational. This list only generates a possible set of rational zeros. So if you have irrational zeros, they're not going to show up on the list. So you have to find those pretty much using the quadratic formula. Now, if you have more than 2 of them, then you might run into some trouble, okay? For the sake of this class, I'm only going to give you problems that have 2 that wouldn't show up on that list. Fair enough? Because otherwise, you'd have to get really lucky to be able to find them. Or you'd have to use technology that you don't have access to, i.e. a graphing calculator. Anyway, so that's okay that those 2 didn't show up on the list because they were not rational to begin with, but they still are zeros of this function. Okay. Solve x to the 4th minus 6x squared minus 8x plus 24 equals 0. Hopefully you understand that that's the exact same thing we've just been doing. Just looks, it's worded a little bit differently. So, how could we proceed? P over Q. 24's got a lot of factors, doesn't it? Bam! Luckily, this is just plus or minus 1. So we have a lot of possibilities, right? Can I make a suggestion in the interest of time? Can we try 2? Let's try 2. All right, so if I put a 2 there, what goes across the top? If you miss that 0, you're going to be hopelessly screwed. You won't even know it. We understand why the 0 has to go there? Yeah, the cubic term is missing. And remember, always double check. If this is x to the 4th, there should be 5 numbers going across there. All right, so let's see what happens. So this would be 1. Woohoo! It works. Imagine that. So maybe if I make a list over here, pick a different number. 4. Now here's the thing. This isn't quadratic, is it? So when you want to check this, you want to check the new quotient, okay? Because essentially what you've done is you've already factored out x minus 2. You don't want to go back to the original. You want to try to narrow this down so that eventually you can get it to a quadratic. Does that make sense? So go off of the new one, not off of the original. Pretty sure that didn't work. The reason why I had you pick another number is to illustrate the fact that if you get one that doesn't work, you're going to go back to this last step that did work. Okay? And notice I didn't work with the remainder at all. That's gone. So when I pick another number, I'm going to go back to the step that I worked with before. Does that make sense what I'm saying? Okay. Now, let me make a suggestion. Let's try 2. Just because it works once doesn't necessarily mean it won't work again. Now, I can promise you this. On the test, I didn't put any on there like that because I don't want you to sit there and waste a bunch of time. The goal is to see if you know how to do this, not to see how fast you can do it. So on the test, I didn't put one on there like this. So 2 worked twice. You know what that means? Think about it. So that means that the multiplicity of the 0 at 2 is 2. Now, if we scroll back down to here, I've now got a quadratic. Whereas if I had started over, if I had gone back to this original and kept going, I'd never be able to get it down to a quadratic, and I'd never be able to find the other 2 because the other 2 happen to be imaginary. So they're not on the list. So if you don't do this step by step, you're probably not going to be able to find all. You've got to narrow it down every step you go. Does that make sense what I'm trying to say there? Okay. So we use the quadratic formula on that puppy. This would be -4 plus or minus the square root of 16 minus 24 all over 2. Square root of -8 is 2i squared is 2. So if you reduce everything by 2, you get 2 plus or minus I squared is 2. I think I forgot to say -2. -2 plus or minus I squared is 2. Now let me ask you this. How many zeros did we actually end up with? 3. But if you account for the multiplicity, it's actually 4. Because this one counts twice. So the one that has multiplicity 2 counts twice, and then you've got 2 more. So that's 4. Well, if you haven't figured it out by now, that's always going to be the case. Whatever the degree of the polynomial is, it's going to have that many zeros. Now, they might not all be distinct. Clearly, these weren't. But if you account for multiplicity, the number of zeros and the degree will always match. And that's actually what's stated in the fundamental theorem of algebra. Whenever something says fundamental theorem, that's when you sit up and pay attention, because that's like whoa dang important. If f of x is a polynomial of degree n, where n is greater than or equal to 1. Because obviously, if it were degree 0, chances are it wouldn't have any zeros because it'd be a horizontal line, it probably wouldn't cross the x-axis. Then, f of x equals 0 has n roots, or n solutions. In other words, it has n zeros. And of course, the disclaimer here is some may be repeated. And that's basically what I've been kind of hinting you or pushing you towards this whole time, is that the number of zeros always matches the degree. Always. That's why when we were doing those sketches of the graphs in 3.2, and I told you to look at the multiplicities, and if you added all the multiplicities up, you could get the degree. This is what told me that was true. Now, I can't prove this to you. Well, I could, but it would require me probably 2 semesters worth of abstract algebra to make it happen. That's like a graduate level, or maybe not a graduate level, but it's an upper level college math course.